Let's now apply the ideas of the potential energy associated with multiple charges to a problem. Our problem has Q1 minus 2C fixed at the origin of this imaginary axis, and Q2 is 1 coulomb, that's a distance A away from the minus 2 coulomb. And then we have a position 3A. And we're going to take a charge Q3 and bring it in from infinity so that it arrives at 3A. So we're going to move Q3 from infinity all the way to this location. And what we're going to do is figure out the work required to do that, keeping in mind that the work required by that external force, namely, say you are grabbing this object and forcing it to move from infinity to 3A. That work to move it from infinity to 3A is the same as the work by the conservative force to move it in the opposite direction from 3A to infinity. Those are always opposite. It's really important to understand this. If not, look at the previous slide. But it's pretty easy conceptually. But just to expand on that a little bit, from infinity to 3A, this is the actual direction that this is being moved. So let's just focus on that. We're from here to here. So the difference between the work done by the conservative force and the external force. Conservative force is just negative delta U. So that's U of infinity minus U of 3A. So that's minus U at 3A. That's what that evaluates to, because U at infinity is 0. So this gives us the work done by the conservative force, or negative U. Now when I just write negative U, it's really the negative potential energy of the charge at 3A, Q3 at 3A. And that's consistent with what we talked about for gravity as well. The work done by the external force is just going to be the opposite of that. So in fact, that's what we're trying to find in this problem. The external force moving it in. It's just change in potential energy. U of 3A minus U at infinity, which is U at 3A, which is equal to U. I guess the other thing I didn't say is when we write U here, or minus U, this is always with respect to infinity. So it's U sub 3A, you could say, which means the potential energy at 3A with respect to infinity. The work done by the conservative force and the external work have opposite signs. That'll always be true. Just like for gravity, we define the potential energy as the amount of work done by the conservative force. For gravity, it was, the gravitational force, as the mass, or in this case the charge, is moved from the current place to infinity. So for gravity, the current location here, and move it to 3A, well, it's trying to be pulled by gravity. So that work by gravity would be positive. If you move it from here to here, it's negative. So the conservative force work and the external force work, they'll have the same signs if the directions are opposite. So that's another way to think about it. Well, hopefully that's not too confusing. Let's solve this problem and sort this out as necessary. Okay, so we are looking for the solution for the potential energy. It was the work done by the external force. And we just saw that that's equal to U, not negative U. And U for multiple charges is this formula that we recently derived, essentially. And the thing that's common is Q3. Q3 is going from infinity to 3A. So that's associated with both of these charges. So KQ3 times, individually, Q1 over its radius and Q2 over its radius. So carried out, KQ3, Q1 over R13 is Q1, this radius, and Q2 is the 1 coulomb, this radius r23. So more quantitatively then, specifically, Q1 is -2, and its distance between Q3 and Q1 is 3a, and then +1 and 2a. There we go. Now, this is -4/6, and this is +3/6. That gives us -1/6. Therefore, the potential energy, -Q over 24 pi epsilon 0a. What we see here, we don't know what Q3 is. I didn't tell you what the sign of that charge was. Well, if it's positive, what this says is that the work is negative. If this is positive, the U is negative in total, which is basically saying that you have this -2c that dominates over this system of 2 charges, so that the external force is back and toward, I guess, infinity, or away from this position. You're holding it back as it's being drawn in toward this position. So the external force, the external work done is negative. If this charge is negative, then you have to shove it toward this position. Again, meaning the -2c is dominating over the +1 coulomb. And so we have positive work done. Again, you can see from this scenario that the -2 coulombs for this particular problem of moving it to 3a has a greater effect on what happens than the +1 does. Now that would change if we happen to have this really close to the 1, because a lot happens at those very short distances. And so very quickly, the +1 would suddenly start dominating over the -2 if we have to get real close to the +1. But that's another story. Now, let's figure out the potential of the system. So we can plug in the basic formula, K factors out, and we have all the combinations. So what are the combinations? They look like this. We have Q1, Q2. So for the whole system in this configuration to be separated to infinity, we have the interaction between these two. That's Q1, Q2 over R12. We have Q1, Q3. So these two with a separation of 3a. And then we have 2 and 3 separated by 2a, it turns out. So let's put that in here specifically. We have -2 over a plus -2 times Q3 over 3a, and +1 times Q3 over 2a. Let's continue to solve this. So if we combine terms and do a little algebra, find the least common denominator, we should get this result here. 6a is the least common denominator. We have -12, and Q3 -4 and +3. This is minus Q3, giving us the potential energy of the system minus 12 plus Q3 over 24 pi epsilon 0a. That may or may not be very intuitive. If you look at this system very carefully, it just might be. Well, in any case, I keep looking outside, and as I record this in January of 2013, we have our first inch of snow, so I see it white outside, and it's really beckoning me. And now my friend just called me, and his neighbor cut a maple tree down, so I'm really itching to go get that maple tree. So let's get a move on this and finish this problem. The thing we have to do yet is figure out the following. Let's assume 0 system energy. So this is the formula for this problem for the potential energy of the system. For it to be 0, what do we need Q3 to be? What charge are we going to put here? Well, that reveals itself very clearly that we make this -12, in which case the whole energy of the system will be 0. So this system here, if we move all the charges mutually out to infinity, and it doesn't matter what direction we move them, as long as they're not in the same place, and they're each mutually infinity away. It's all that matters, and there's really a potential infinite number of solutions or particular ways to move them. Then it takes no work to do that. It's kind of a weird idea. So the total system energy, you take all three, move them to infinity, and because of the nature of potential energy being a scalar type quantity, it's not dependent on direction. So it really doesn't matter. We could take this and move it this way to infinity or this way, and same thing for all these. Now let's assume that Q1 and Q3 are fixed. So these two are fixed, and we're going to let this 1 Coulomb charge move between them. In fact, we're going to let it accelerate from A to 2A. Now, will it do that? Well, to answer the question, let's see. This is half the distance of this. So this double distance means the electric field is quartered from that double distance. So this charge would have to be 4 times as big as this charge to have the same effect. Well, it's 6 times as big. So in fact, 1 Coulomb, it really would accelerate toward the -12. All right. Now, how fast will it be moving at this location? Let's solve that. And assume it has mass m. Well, the mechanical energy is conserved here between potential and kinetic. So we can write our energy equation. Ka plus Ua is K2A plus U of 2A. Now, there is no motion to begin with, so that goes away, and we have this result for our kinetic energy, because the speed is going to be contained in the kinetic energy at position 2. So Ua minus U of 2A. So let's do it. 1/2 mv squared. U of A, the potential energy of this charge at A, is the result of its energy compared to the two charges, -2 and -12. So we have to consider the contributions from both. So the Q2, this charge, is common, and we do the multiple charge potential energy. So it's Q1, this guy, over the distance A, plus Q3 over the distance 2A. But then we're going to subtract potential energy at 2A. So when it's over here, we have the same scenario. But now, Q1 is separated by 2A and Q3 by 1A. So we can combine these, and we have the following. When we think of Q1 over A minus Q1 over 2A, that gives us Q1 over 2A. Q3 over 2A minus Q3 over A gives us minus Q3 over 2A. So there we go. So now we can solve for v squared. Multiply both sides by 2, divide by m. Well, Q2 is already just 1. So this gives us 1 for Q2 over, we multiplied by 2. It made the 4 into a 2. And we divided by m. Q1 is -2. 2A is 2A. and Q3 is minus Q3, makes this plus 12 over 2A, giving us a speed of 5 over 2 pi m epsilon 0 A. So that was kind of fun. Obviously, that could get very confusing, or maybe not so confusing, but just cumbersome if we have a lot of charges. But now we've been looking at so far potential energy and work with considering point charges. It's now time to transition in the next video to the potential associated with point charges, which is a little bit different than potential energy. Potential is energy divided by the charge. So let us investigate that phenomenon.